let's find the steady state for this 3 by 3 regular Markov process. It's regular, right? Because even to the first power, all the entries are non-zero. They're all positive. So it's regular, so it's going to reach a steady state. Let's find it. So why don't we start here? Let x be this steady state vector. Now it's supposed to be a capital X. This is a lowercase x. So here's a steady state vector. I'm just calling it x. And we know that we can find the steady state vector by solving this equation. Tx equals x. Right? What that does, it takes the transition matrix, applies it to our steady state vector, and what do we get back? The same steady state vector. So here's our matrix equation. Let's set it up and multiply through. We are going to get, let's write this. I'm going to write down the columns. 0.6, 0.1, 0.3, 0.4, 0.3, 0.3, 0.5, 0.2, 0.3, times that steady state vector, x, y, z, and that's going to give us back that steady state vector, x, y, z. So let's multiply. We'll get 0.6x plus 0.4y plus 0.5z, right, over and down. First and first, 0.6x plus 0.4y plus 0.5z. I'll just do the rest of them. And this can be 0.1x plus 0.3y plus 0.2z, and then 0.3x plus 0.3y plus 0.3z, right? That's the multiplication of those two matrices on the left side, the equal sign. And this is equal to our steady state vector x, y, z. And we know two matrices are the same if their components are the same. So we're going to get these equations here, right? This component here equals that component. The second equals the second. So let's write this. We'll get 0.6x plus 0.4y plus 0.5z. That's equal to x. 0.1x plus 0.3y plus 0.2z. That's equal to y. And 0.3x plus 0.3y plus 0.3z, that's equal to z. All right, there's our system. But now we know that when we solve systems, we have all the variables, say, on the left side and constants on the right. So let's subtract x, subtract y, subtract z. So we'll have zeros on the right side. Let's do that. So when I subtract the x, I'll have 0.6x minus 1. Now 0.6 minus 1 is negative 0.4x plus 0.4y plus 0.5z. That's all equal to 0. Okay, are you okay with the negative 0.4? I got that from here, right? 0.6x minus x. I'll do it down here. What if I had this? 0.6x minus x. It's really 0.6x minus 1x, and then it's really like this, 0.6 minus 1x, which is negative 0.4x. Or if you like, you could make everything, get rid of the decimals. This would be 6x minus 10x is negative 4x, and just make it a decimal again. Then in the second equation, let's subtract the y. So I'll get 0.3 minus 1. So here's what we're going to have in the second equation. 0.1x. Now, 0.3y minus y, negative 0.7. Negative 0.7y plus 0.2z equals 0. And in that third equation, what I'm going to do here is I'm going to subtract the z. So I've got a 0.3 minus 1 is another negative 0.7. So that third equation is going to be 0.3x plus 0.3y minus 0.7z equals 0. There's that system. Now, just like in the 2 by 2 that we did, this system is going to have no unique solution. And you can see that if you look here. What do you get if you add these first two equations together? What do you get here? Negative 0.3, there's the 0.3, negative 0.7, positive 0.3, 0.7, negative 0.7. These numbers here are just the sums of these, but they're opposites. It's like you could add these together and then just take the opposites. The third equation is just a combination of these two. So here's what we're going to do. This works every time. If you have a 2 by 2, toss out one equation. If you have a 3 by 3, toss out one equation, and it doesn't matter which one. If you had a 4 by 4, toss out one equation. It doesn't matter which one. So I'm going to keep the first two. I'll take negative 0.4x plus 0.4y plus 0.5z equals 0. And the next one, 0.1x minus 0.7y plus 0.2z equals 0. And I'm going to toss out that third equation and replace it with, what do you know here? Right? What am I going to do? I need an independent equation. That's going to come from here. Right? These are stochastic. So if I add these up, I get a 1. So that always happens. You add those, you get x plus y plus z equals 1. There's our system. Let's put it into a matrix and RREF this. So what I'm going to do here is I'm going to RREF this matrix. I'm going to go down the columns. Negative 0.4, 0.1, 1. 0.4, negative 0.7, 1. 0.5, 0.2, 1, and I'll draw the line there, 0, 0, 1. So it's just RREF, that should give us our steady state vector. And when I did that, here's the matrix I got. You know, we always get our 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. And then I'm going to round off that first one. I got 0.5375. I'll make it 0.54, and then 0.16, and 0.30. And sure enough, those add to 1 or very close to it. So I'm going to say then our steady state vector for this 3 by 3 system is 0.54, 0.16, 0.30 for our states x, y, and z.